Okay, so good morning. Our today's topic is NEET questions of coordination compounds. So let's begin. So this is the first question on your screen. Question is that correct increasing order of our today's topic is correct increasing order for the wavelength of absorption in the visible region for the complexes of cobalt 3 plus. So complexes of cobalt 3 plus, and we have different ligands. See, there is H2O in the first case, ammonia in the second case, and ethylene diamine in the third case. Now just see the spectrochemical series. So according to spectrochemical series, out of these three, H2O is weakest ligand and En is strongest out of these three. Means order according to spectrochemical series, H2O is weakest, then comes ammonia and then En. So according to this series, when we have octahedral complex, d orbital split into T2G and Eg, and this is the difference between the two. So delta O is maximum for En and minimum for water, right? So that delta O is inversely proportional to lambda. Am I right? Because delta O means energy difference between T2G and Eg. So when electron shift takes place, this is the energy. So this energy is maximum for En, and energy is equal to h nu is equal to hc over lambda. So energy and lambda is inversely proportional. Got it? Energy and lambda is inversely proportional. So wavelength, if we compare delta O value of third is maximum and for first it is minimum. Means for delta O order is third is greater than second is greater than first, and if we compare lambda values, so lambda value of obviously first is greater than second is greater than third, right beta? Got it? That means order is CO H2O6 correct increasing order. That means increasing order of this is the decreasing order. If we do like this, that means increasing order is increasing order of wavelength. So first of all it is okay, CO En thrice, then CO NH3 6, and then CO H2O 6. This is the increasing order. Okay. Yes. So now question number 2. Which of the following has the longest CO bond length? Free CO bond length is given to you. Now I'm all right beta karna. Okay. So see, in CO CO has bond order as 3. Bond order of CO is 3. Okay. So in CO, if you write its actual thing, it is like this. CO is a ligand, okay, and it donate electron pair to vacant orbital of metal to form sigma bond. Okay. So this is the due to lone pair on the CO, on the carbon of CO, and at the same time, as CO is neutral, filled orbital of metal overlap with vacant orbital of CO. Okay. So when this filled orbital of metal back donate its electron, this is called back donation. Okay. Or if it is D, it is D pi P pi back bonding, and due to this back donation, electron is accepted by CO, and if CO accept the electrons, you know, in CO electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi. Actually it is not like this, there is sp character, but we are writing it in the simplified version, sigma 2pz 2 because it has 14 electrons. So 2 plus 2 4, 4 6 8 10 12 14. Okay, then it is pi star 2px 2py sigma star 2pz. That means when it accepts the back, means when metal back donates electron, that electrons are accepted by pi star orbital. There is some sp character, keep in mind. Okay, there is sp character. Okay, but anyhow, see, due to back donation, what happened? Electrons are entered in, yes, electrons are entered in pi star orbitals, okay, of CO. So when electrons are entered in pi star orbital, then what happened? Bond order, yes, bond order decreases and bond length increases. Bond length increases. Very good, Tirth Patel. Bond length increases. Okay. So that means we should look at the question and see which of the following is longest. That means bond length is longest where bond order is lowest. Lowest CO bond order. And bond order is lowest where maximum back donation is there. Maximum back donation. So see, here there is a positive charge, so back donation is minimum because that positive charge is on the metal. Okay, because CO is a neutral ligand. Here it is neutral. Here there is a negative charge, one negative on CO. In this case, there is two negative on CO. When there is two negative on Fe, then back donation is maximum because it is more electron rich. Back donation is maximum. As back donation is maximum, so bond order is lowest because that electron is donated to pi star orbital. Okay, and that's why bond order decreases and bond length increases. So fourth option is correct. Yes, beta. All right. Means whenever there is a question related to this topic, keep in mind in free CO, see, free CO there is no back donation, because keep in mind whenever we have a CO, CO is a pi acid ligand. In free CO, bond order is 3. But when back donation takes place, more is the back donation, more is metal carbon bond strength increases, and carbon oxygen bond length increases because its bond strength decreases. See, more is the back donation, this bond becomes stronger and this bond becomes weaker. That's it. Okay, question number 3. Which one of the following is in an outer orbital complex? Which one of the following is an outer orbital complex and exhibits paramagnetic behavior? Now, first of all, keep in mind that this ammonia is a borderline ligand. Means it is not very strong, not very weak. Ammonia can form outer orbital complex as well as inner orbital complex depending upon the metal. Okay. Now see, in chromium 3 plus, let us write it like this. T2G and Eg. Now, in first case there is chromium 3 plus. You know, chromium is 3D5 4s1. So, as chromium is 3D5 4s1, so what is chromium 3 plus? It is 3D3. So, you know, 3D3 means Eg is always vacant. So, it has always inner orbital complex. It is always an inner orbital complex. So, it is out of picture. Now, come to cobalt. Cobalt is 3D7 4s2. So, cobalt 3 plus, it is 3D6. Okay. So, you know, it is like 1, 2, 3, 4, 5, 6. But, you know, if these 2 electrons come here, it becomes T2G6, most stable, right? That's why it is also an inner orbital complex. And hybridization is here D2sp3, D2sp3. And this is paramagnetic because in that case 3 electrons are unpaired, and in cobalt means hexamine cobalt 3, it is diamagnetic. Now come to nickel. In case of nickel, you can see it is 3D8 4s2. So, nickel 2 plus it is 3D8. So, 3D8 means it is like this. Now, anyhow, it can never form D2sp3 hybridization because 2 d orbitals are not vacant at the same time. So, obviously, it is outer orbital complex. Hybridization becomes sp3d2 and these 2 electrons remains unpaired. So, it is the right option. If you compare with zinc, you see in case of zinc, it is 3D10 4s2. So, Zn2 plus it is 3D10. All the inner d orbitals are filled, and it is also outer orbital complex but diamagnetic. Outer orbital but diamagnetic. This is outer orbital but paramagnetic, and that is what needed in the question. Beta, this third question is clear to you? Any doubt in this question? See, just write the electronic configurations. When you write the electronic configurations, you come to know that it is 3D3, 3D6, 3D8 and 3D10. Okay. Now, question number 4. An excess of AgNO3 is added to 100 ml of 0.01 molar solution of dichlorotetraquachromium 3 chloride. So, number of moles of AgCl precipitated would be, see, we have AgNO3 in excess plus dichlorotetraquachromium, dichlorotetraquachromium, better to write aqua first, dichloro, yes, because chromium is 3 plus, so there is only one chlorine left outside, and we get AgCl, okay, along with, because only chlorine which can be ionized is outside the bracket. So, this is the product formed. So, that means that this is the limiting reagent. So, limiting reagent is the one which is consumed completely and decides the amount of product formed. So, number of moles of this complex is equal to molarity into volume in ml divided by 1000. So, molarity is, yes, what is the molarity? 0.01 and volume is 100 and divided by 1000. So, 2, that means it is 0.001. So, if it is 1 mole, then we get 1 mole of AgCl. So, if it is 0.001, it should be consumed completely. So, we get 0.001 mole of AgCl. So, that is equal to number of moles of AgCl formed. So, number of moles of AgCl precipitated would be obviously option 0.001, that is option 4 is correct. Okay. Done. So, now question number 5. Yes, red PPT is obtained when ethanolic solution of dimethyl glyoxime is, dimethyl glyoxime is added to ammoniacal nickel 2. So which of the following statements is not true? You know, nickel DMG complex is formed when nickel 2 react with DMG, then we get nickel DMG twice. Okay, so obviously it is a red colored complex. Okay, and the complex formed is like, see, I will write the structure. Nickel 2 plus, so N double bond C, C double bond N, CH3, CH3, O negative and N positive, and it is OH. Same on the other side, N double bond C, double bond N, CH3, CH3, OH, O negative and positive. So there is a hydrogen bonding like this. The symmetrical hydrogen bonding is there, and formation of 4 coordinate bonds with nitrogen. Okay, so in this way it has square planar complex, it is red colored, and dimethyl glycoside, you can write DMG, is bidentate ligand. It is bidentate ligand. Okay, so you can see first red complex has a square planar geometry, right? Complex has symmetrical hydrogen bonding, right? But red complex has tetrahedral geometry. Obviously out of 1 and 3, 1 is incorrect. Okay, so it is actually square planar complex. Okay, so it should not be tetrahedral. So obviously third option is correct, because we have to identify the incorrect statement. Dimethyl glycoside function as a bidentate ligand, right? Because question was which of the following statements is not true. So it should be third statement, which is not true. Yes, Swasti? Is it okay? Understood? Question number 5. Yes, beta. Now question number 6. Low spin complex of day 6 cation in an octahedral field will have the following energy. We have to calculate the energy. Okay, so again complex is octahedral, so obviously splitting is T2G and EG. In T2G there are 3, and now from that very center This is very center. So it is plus 3 by 5 delta O, and it is minus 2 by 5 delta O, right? According to CFT, crystal field theory, it is like that. So D6 cation, low spin. Low spin means inner orbital complex. So it is 1, 2, 3, 4, 5, 6, because already mentioned it is a low spin complex in an octahedral field. So that means there are 3 paired electrons, means there are 3 electron pairs. So from it we get energy as 3p, because see, p is the electron pairing energy. So if there are 3 pairs, we write plus 3p. Now come to second part, that is in terms of delta O. So for one electron it is minus 2 by 5 delta O per electron, and total electrons are 6. So it is minus 12 by 5 delta O plus 3p. That's it. So that means option 2 is correct. Is it okay? See, crystal field splitting energy is given to you, that is delta O, and from the very center T2J is minus 2 by 5 delta O, and EJ is plus 3 by 5 delta O. So just multiply minus 2 by 5 delta O into number of electrons, that is the energy in terms of delta O, and as 3 electrons are, means 3 pair of electrons are there, so 3 into number of electrons paired. Okay, so 3 into P. Okay, total electron paired are 3, and electron pairing energy per pair is capital P. So plus 3p. Okay, so this is question number 6. So see, if you have any doubt, please do ask anytime. Okay. Yes, the complex platinum pyridine NH3 BrCl. So keep in mind any complex of this type, that is M attached to A, B, C, D, means all the 4 different ligands. So there are total, always there are 3 geometrical isomers. It is like this. It is very important question. A, fix A, and there is a B, C, D. Fix any one of the ligand. A is fixed, we rotate it clockwise or anti-clockwise. C, D, B. A is fixed, C, D, B. So there are total 3, because if we rotate once again, then we get this one. So there are total, always whenever we have a complex in which metal is attached to 4 different ligands, then we have total 3 isomers. That's it. Okay, question number 8. Which of the carbonyls will have the strongest CO bond? But where are the options? Okay, wait. Okay, so first is VCO6 1 negative, second is FeCO5, third is MnCO6 1 positive, and fourth one is CrCO6. Yes. Now, which of the following carbonyls will have the strongest CO bond? CO bond strongest, and you know bond strength is proportional to bond order. Bond strength is proportional to bond order and inversely proportional to bond length. And you know, when back donation is more, bond order is less. So strongest bond means, strongest. CO bond is strongest. So strongest means CO bond order is maximum. That means CO bond length is minimum and back donation should be, yes. Swasti, tell me, back donation is more or less? To have maximum bond order, bond donation is, back donation is more or less? Very good, yaar. Tirth Patel, you are great. Tell me, Swasti, back donation is more or less? Back donation should be, means back donation from the metal is, should be least. Very good, least. Okay, so see, there is one negative, there is neutral, this is also neutral, but there is positive charge. So obviously when it has positive charge, back donation is less or little chance of back donation. That's why third option is correct. Okay. See, if we have weakest CO, then it should be first, because back donation is maximum if metal has a negative charge, and if metal has positive charge, then its back donation is least. Okay. Now question number 9. Which of the following complex ion is not expected to absorb visible light? See, if we have vacant or partially filled d orbital, then there is a chance of absorption of light, because then electron can shift in that particular region. Okay, so now see, in nickel 2 plus it is 3d8, in chromium 3 plus it is 3d3, and Fe2 plus it is 3d6. Oh sorry, and it is nickel 2 plus again, and nickel 2 plus 3d8. Now see, these three are they have see this is always outer orbital complex, and 3 electrons are always unpaired. 3 electrons are always unpaired. In this case, again this is outer orbital complex because water is weak ligand. Here again outer orbital complex, and they have, sorry, this is inner orbital complex, but there are 3 unpaired electrons. But in case of nickel 2 plus, there is cyanide. It is a strong ligand. As it is a strong ligand, obviously it is not tetrahedral. It is DsP2 hybridization. All are paired. Okay. And because of this strong ligand, this complex will not absorb light in the visible region because all the orbitals are filled either by metal line electrons or cyanide. That's it. Got it, beta? Then nickel cyanide complex, because cyanide is a strong ligand, so pairing takes place, and that's why there is no chance of a rearrangement of electrons, d electrons. Done? Here see, there is water and there is cyanide. So this is the basic reason. Okay, crystal field stabilization energy for high spin D4 octahedral complex. Octahedral T2G EG D4 high spin. D4 high spin means maximum unpaired electrons. Same from barycenter, it is plus 3 by 5 delta O minus 2 by 5 delta O. No paired electrons, so P is not there, okay. But now calculate the crystal field stabilization energy. There are 3 electrons in the T2G, and per electron energy is minus 2 by 5 delta O, plus there is 1 electron in the EG, and per electron energy is plus 3 by 5 delta O. So it is minus 6 by 5 delta O plus 3 by 5 delta O. That means it comes out to be minus 3 by 5 delta O, or we can say minus 0.6 delta O. So option 4 is correct. Yes, I think it is very simple question. You can do it now, because earlier we have done question like this. If it is low spin, see, if it is low spin complex, then it should be like this, and this part is vacant. So in that case, it becomes 4 into minus 2 by 5 delta O, and there is one pair of electrons, so plus P. That means it becomes minus 8 by 5 delta O plus P. That is minus 1 point, yes, minus 1.6 delta O plus P. So for low spin D4 complex, value comes out to be minus 1.6 See, minus 1.6 delta O plus P. So that means if it is low spin, then value comes out to be second. Option second is correct, but it is given high spin. So it is minus 0.6 delta O. Yes, beta. Swasti. Okay, now question number 11. John Taylor effect is not observed in high spin complexes. Yes. Now complexes high spin. Keep in mind John Taylor. Okay, wait. Say in this case we have 4 electrons. Out of 4, 3 are in T2G. There are 3 electrons, and for each electron energy involved is minus 2 by 5 delta O. So minus 2 by 5 delta O into 3, and 1 multiplied by 3 by 5 delta O. But if it is low spin, then what happened? Electrons are paired. So total electron are 4 in T2G. So 4 into, for per electron it is minus 2 by 5 delta O. So 4 into minus 2 by 5 delta O, and 1 paired electron is there. So pairing energy is P per pair. So there is only one pair, so plus P. So it is minus 8 by 5 delta O plus P. So value comes out to be minus 1.6 delta O plus P. Okay. Now John Taylor effect. See, there is a little in your syllabus, but John Taylor effect means if T2G is unsymmetrical. T2G is unsymmetrical, then there is weak John Taylor effect. Second, case 2, if EJ is unsymmetrical, then there is strong John Taylor effect. If T2G as well as EG are symmetrical, then no John Taylor effect. Only keep this thing in mind. Symmetrical means either T2G3 or T2G6, EG2, EG4. They are symmetrical, except that all other are unsymmetrical. That means EG1, EG3, they are unsymmetrical. T2G1, T2G2, T2G4, T2G5, they are unsymmetrical. Now, given no John Taylor effect, John Taylor effect is not observed in high spin complexes of first D7. D7 in high spin. Yes, it is 1, 2, 3, 4, 5, 6, 7. See, here EG is symmetrical, but T2G is unsymmetrical, right? So that means it will show John Taylor distortion. Now come to D8. Good morning, Ashish. T2G and Eg. In case of D8, it is 1, 2, 3, 4, 5, 6, 7, 8. See, T2G is symmetrical, Eg is also symmetrical. That means D8 in high spin has no, D8 in high spin as well as low spin, both, it is symmetrical. So, it will not show John Taylor distortion. D4, yes, D4, 1, 2, 3, 4. So, T2G is symmetrical, but EG is unsymmetrical. Okay, and D9, in D9, yes, D9, 1, 2, 3, 4, D9, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. EG is unsymmetrical. So, D7, D4, D9 will show John Taylor distortion, John Taylor effect. But in case of D8, there is no John Taylor effect. Means John Taylor effect is not observed in D8 high spin complex, in D8 complex. Okay. Yes, Swasti, question number 11. Now, the pair of compounds that can exist together. This is the technically tough question, but you can easily figure out. Okay, wait. See, John Taylor effect, it is shown by those compounds or those complexes in which there is unsymmetrical distribution of electrons in T2G and EG. Okay, if T2G as well as EG both are symmetrical, means distribution of electron is symmetrical, then there is no John Taylor distortion. John Taylor effect is not observed. Now, when we compare, in case of D7C, 1, 2, 3, 4, 5, 6, 7. So, see, T2G is unsymmetrical because either all of them has 2 electrons or 1, 1, 1. But here there are 2 are paired, 1 is unpaired. So, it is unsymmetrical, but here in EG both the electrons are unpaired, means it is symmetrical. So, obviously John Taylor effect is observed. But in D8, see, all the T2G means orbitals have 2 electrons each. So, that means it is symmetrical, and each EG orbital has 1 electron. So, it is also symmetrical, means both T2G and EG are symmetrical. So, John Taylor distortion or John Taylor effect is not observed. Is it okay? But in D4, D9 again there is unsymmetrical arrangement. Like in D4, obviously in T2G it is symmetrically arranged, but in EG there is 1 electron and other is vacant. So, it is unsymmetrical and this one is symmetrical. Okay. Now, question number 12. The pair of compounds that can exist together is, see, if we have Fe, Fe is 2 plus and 3 plus, Sn is 2 plus and 4 plus. These are the oxidation states, common oxidation states, lower one and higher one. Ashish, you are wrong, beta. See, so when we have FeCl3 along with SnCl2, there is a chance of formation of FeCl2 and SnCl4. Even Hg is there. So Hg is 2 plus as well as Hg2 2 plus, Hg2 plus, means it is 1 plus and 2 plus. Again, see, here is higher oxygen state, lower oxygen state, reaction can take place. It is higher, I will write H and L, okay. Higher oxygen state, lower oxygen state. In this case, higher oxygen state, because Hg2 2 plus means Hg1 plus is lower, higher lower. Here lower lower, higher, and iodine is -1 lower. That means in first, second and third there is higher and lower oxygen states. So redox reaction can take place. One can increase the oxidation number, other decrease the oxidation number, means there is an increase and decrease in oxidation numbers. But if both are in lower oxidation state, they will never react with each other. And so third option is correct. Okay, beta. How can we go? How can we solve it? If there are both higher oxidation states or both lower oxidation states, so they can exist together. But if it is one higher and other lower, very good, Ashish, then there is a chance of reaction and they cannot exist together. Okay. Now question number 13. For the 4 successive transition elements, chromium, manganese, iron, cobalt, the stability of +2 oxidation state will be there in which of the following order? This one is the toughest question, keep in mind. Reason being, see, chromium, manganese, iron, cobalt. Okay, chromium is 3d5 4s1, 3d, yes, 3d5 4s2, 3d6 4s2, 3d7 4s2. Okay. Now 2 plus, chromium 2 plus, 3d 4, manganese 3d5, 3d 6 and 3d 7, and M3 plus, 3d 3, 3d 4, 3d 5 and 3d 6. That's it. So now if you compare the stability, obviously it looks like, it seems like, which one is most stable out of this? In 2 plus state, which one is supposed to be most stable? Actually, as we go along the series, yes, so Mn2 plus seems like most stable because it is 3d5, and 3d5 means all the 5d orbitals have 1 electron, right? wait beta. Okay, so now it seems like most stable is manganese, then chromium, iron, cobalt. Okay, but see, chromium in 3 plus state, it is 3D 3, so it become more stable. Okay, that's why chromium is not in the front list. Okay, um, 1 second, please wait for a few seconds. Okay. Oh. See, it seems like manganese is more stable. Okay, then chromium, then iron, and last is cobalt. Actually, it is comparable from the E naught values. Okay, so down the group, actually 2 plus state becomes, yes, 2 plus state becomes less stable. Okay, but see, if you compare chromium, so chromium 2 plus, it easily turns into 3 plus because it becomes 3D3. So that's why Mn, after Mn there is iron and then chromium. Otherwise chromium should be after manganese, but because chromium 2 plus can be easily converted into chromium 3 plus because it becomes 3D3. Okay, that's why chromium goes after iron. Okay, because in iron it is 3D6, that is more stable than 3D5. Okay, that's why iron is before chromium, and you can cobalt, 3 plus is 3D6, that is more stable, less stable, that's why cobalt is at the end. So manganese, then iron, then chromium, then cobalt. So option 2 is correct. Ashish, very good. Swasti, this is, I think, a toughest question you are not able to figure out because it is a difficult one, because you have to compare first E naught value of M2 plus 2M and then E naught of M3 plus 2 M2 plus, but it is difficult to remember those values and at the same time not able to figure out clearly. But keep in mind that option 2 is correct, that manganese is in plus 2 state is more stable than Fe2 plus, and then chromium and cobalt. Okay beta. Now okay, number of moles of MnO4 negative required to oxidize 1 mole of ferrous oxalate completely in acidic medium will be. So see, MnO4 negative in acidic medium, it is turn out to be, okay, wait. See, in question number 13, there are 4 successive transition elements First of all, you compare like this. See, Mn2 plus is 3d5. So, it is most stable, okay, because its value E naught value means we can compare it with E naught values actually. So, according to data, E naught value of M2 plus 2M for chromium, manganese, iron and cobalt, it is minus 0.9, minus 1.18, minus 0.44 and minus 0.28. So, see, value of M2 plus 2M, it is least for manganese. That means M2 plus for manganese is most stable. Okay. So, and then it comes to chromium and then iron and then cobalt. It according to E naught M2 plus 2M, as we go down the group, keep in mind E naught of M2 plus M becomes less negative, but manganese is an exception because Mn2 plus is more stable, that becomes 3d5. Okay. So, E naught value for manganese is more negative than expected from general trend because of extra stability of half filled electronic configuration. Okay. So, order should be like this: manganese, then chromium, then iron and then cobalt. But if you compare E naught value of M3 plus to M2 plus, then Cr2 plus is strongest reducing agent, and even it can liberate hydrogen gas. Okay, that's why chromium is, because E naught value of this is positive, that is 0.41 volt for chromium. Okay. That's why chromium is after iron. So, order is manganese 2 plus is most stable and then iron 2 plus, then chromium 2 plus and then cobalt 2 plus. Okay. Got it? Swaste? सबसे ज्यादा इलेक्ट्रॉन होते हैं अनपेयर्ड. आशीष, व्हाट इज द क्वेश्चन? सबसे ज्यादा इलेक्ट्रॉन होते हैं. इलेक्ट्रॉन सबसे ज्यादा तो लास्ट वाले में होंगे 120 एटॉमिक नंबर वाले में. Mn2 से in acidic medium MnO4 negative converted into Mn2 plus balance the oxygen 4H2O 8H plus 5 electron, right? Now come to next part, that is ferrous oxalate. Ferrous oxalate is Fa2 plus and oxalate is C2O4 2 negative. So, ferrous oxalate in it is like this. So, ferrous is turned into ferric, oxalate into carbon dioxide. So, ferrous oxalate is Fe3 plus 2 CO2 plus 3 electron. Okay. Here there are 3 electrons, in MnO4 negative 5 electrons. So, it should be multiplied by 3 and it should be multiplied by 5. That means 3 mole of MnO4 negative oxidizes, sorry, 3 moles of MnO4 negative, oxidizes 5 moles of ferrous oxalate. Okay, and what is the question? Question is number of moles of MnO4 negative required to oxidize 1 mole of ferrous oxalate. Okay. So, to oxidize 5 moles, 3 moles are required. Three moles of MnO4 negative ions are required, and to oxidize 1 mole of ferrous oxalate, 3/5 moles of MnO4 negative ions are required. 3/5 means 0.6 moles of MnO4 negative are required. Sorry. So 0.6 means option 2 is correct. Option 2 is correct, right? Now, question number 50. Which of the following is the most stable in aqueous solution? Mn2 plus is 3d5. It is 3d3. B3 negative. It should be 3 positive, I think. Maybe 3 negative if it is like this, but it is, I don't know. 3 positive, keep it. So vanadium is 3d3, 4s2 means 3d2, and it is 3d, yes, titanium 4 plus 3d0. Right? Mn2 plus, Cr3 plus, and vanadium 3 plus, and titanium 4 plus. Yes, any guess? Yes, beta. Any guess? Most stable in aqueous solution. Three D titanium is 4 plus. With titanium is 3d2. It is plus 3 na. Okay. So it should be Mn2 plus, because in aqueous solution it is like this, because low spin complex. So symmetrical arrangement of D5. So obviously Mn2 plus is more stable. Yes, beta, right. Okay. Done. Let's go to the next question. Any doubt in this question? Yes, beta. It is because extra half filled, exactly half filled and fully filled electronic configurations have extra stability. Now question number 60. Basic character of the transition metal monoxides follows the order titanium, vanadium, chromium, iron. Yes, beta. Half filled orbital, because of the half filled orbital. Yes, in aqueous solution, then we can say that the weak ligand, because H2O is a weak ligand. Okay, that's why in aqueous solution half filled and fully filled configurations have extra stability, because in half filled, say there is no pairing of electron, high spin complex is formed. So we can apply this, okay, in aqueous solution as well. At the same time, higher charge will also play the role, but configuration and hydration both play the role. Okay, now come to the basic character of transition metals. Yes, so in this case we have titanium, vanadium, chromium and iron. So as you know, atomic number increases, then basic character of the oxides, because as we go along the period, you know, size of cation decreases, because all are 2 plus. So as size of the cation decreases, then its polarizing power increases, it becomes more covalent and less basic, more covalent and less basic. Okay, so that means titanium oxide is more basic than vanadium, and then it is more, which in turn more than chromium monoxide and then iron monoxide. So this is the order. Okay, so keep in mind, as atomic number increases, basic character decreases. Okay, the highest possible oxidation state shown by osmium in its compounds is, so osmium is the only one, you know, that is of the iron series. Ferrous, it is N-1D 6 NS2. So maximum oxidation state is for by osmium is shown by osmium is +8. Okay, and it is the only one which can show +8 oxidation state. OSO4 exists, osmium tetroxide, and has tetrahedral arrangement. Okay, osmium tetroxide. Yes, beta. I think it's the last question. It was the last question. Any doubt? Swasti, beta, got it? Okay, so thank you. Thank you so much for your patience when you learn it. If you have any doubt, please do ask Swasti after this session. Okay, that's all for the day. Thank you so much.